The data revolution is transforming fields as diverse as astronomy, archaeology, and earth sciences. This work depends on and is stored as trillions of data points. Today's data-intensive scientists need to quickly and easily store, analyze, and move these large data sets between collaborator labs, supercomputer centers, scientific instruments, and data repositories. Just as the high-speed, end-to-end, no-stoplights interstate highway system transformed the American economy and social mobility in the 20th century, the big data cyberinfrastructure of the National Science Foundation-funded Pacific Research Platform promises to transform scientific advancement in the 21st century. The PRP superhighways, with network speeds from 100 to 1,000 times faster than commodity internet, are provided by regional optical networks such as CENIC in California and its partner networks, nationally and internationally. PRP's on-ramps to these optical fibers are rack-mounted PCs, each containing powerful multi-core CPUs, up to 8 gaming graphics processing units, and large amounts of storage. Many of these PRP endpoints are drop-shipped to remote campuses, but in California, our UC San Diego technical team used the old-fashioned road trip to visit and install rack-mounted big data endpoints at campuses from UC Santa Cruz to UC Santa Barbara to Stanford University to UC Merced and back down to UC Irvine and UC Riverside. Internationally, these PRP endpoints span from Korea to the Netherlands. In the United States, there are over 180 of these big data PCs located and operational on 25 partner campuses, 10 of which are minority-serving institutions. California is home to the largest number of PRP campuses. Pacific Research Platform users place their application in software containers, and then the PRP uses Google's open source Kubernetes to orchestrate the movement of these containers across the distributed PRP system or into commercial clouds. Because of PRP's aggressive containerization and high-speed networking strategy, to the user, the PRP's over 7,000 CPU cores, 500 GPUs, and 4,000 terabyte storage appear to be in the same room, while being interconnected by CENIC, the Quilt, and Internet 2. The PRP is uniquely designed for working with multi-campus science teams from a wide range of application disciplines. Let's look into 3 examples of the over 400 projects actively using the PRP. Neutrino observatory data analysis, networked virtual reality systems, and prediction of wildfire spreading. A major use of the PRP is data analysis of the massive digital output of observatories. For instance, the National Science Foundation South Pole IceCube Neutrino Observatory is designed to detect astrophysical neutrinos. Spheres containing digital photosensors are attached to vertical strings, which are lowered into the boreholes, where they are frozen in ultra-transparent Antarctic ice. When a neutrino that has traveled across intergalactic space collides with an ice atom's nucleus, it creates a charged particle producing a cascade of blue light, which is detected by thousands of IceCube photosensors. The data analysis of when each of the photosensors detects the blue light provides information on the direction in space that the neutrino came from. Graphics processing units compute millions of photons propagating through the ice. The neutrino data is sent to the University of Wisconsin-Madison IceCube team, who then runs high-throughput computing on the Open Science Grid, OSG, a global distributed system of over 140 computer clusters. The OSG can in turn request usage of the PRP's GPUs. By mid-2020, IceCube data analysis was using nearly half of PRP's 500 GPUs for months at a time. Moving to the second example, modern archaeology is able to capture 3D digital movies on location and convert them into virtual realities. The PRP enables 3D high-resolution images of the ruins of Luxor in Egypt captured by UCSD PRP team to be shown on the UC Merced Wave by pulling the data from UCSD over the PRP to Merced. The same Luxor dataset can be viewed on 2 other virtual reality systems, Qualcomm Institute's Sun Cave on the UC San Diego campus, or the Citrus Cave Kiosk, inspired by the cave kiosk in the Hearst Museum of Anthropology on the UC Berkeley campus. These virtual reality systems are powered by the PRP PCs, which provide nearly 100 of PRP's 500 GPUs, available in standby mode to support the PRP applications such as IceCube data analysis and machine learning. A final example is this public service PRP application developed in response to destructive wildfires becoming the new normal in California. With support from the National Science Foundation over 20 years, the High Performance Wireless Research and Education Network and its partners built out meteorological stations and hundreds of cameras across Southern California. Those sensors constantly stream data into PRP's big data PCs, which are connected by optical fiber networks to the San Diego Supercomputer Center. There, these second-to-second data updates are integrated with detailed topography and fuel loads by the NSF-funded Wi-Fi cyberinfrastructure to better equip emergency responders to model and predict fire behavior using real-time data sources and machine learning models.
The director of Cal IT2, Larry Smar, and the chief data science officer at San Diego Supercomputer, Ilkay Altintash, put those pieces together so how you can make the technology and the hardware and the simulation and data science integrated into a platform that can be seamlessly intuitive to firefighters and the public.
When you think about a location and time that the fire starts, there is a number of data that you can bring together. If you could bring together all the data, you can actually enable fast decision support using models, data science, fire science. So that's what Wi-Fi achieved.
Field resources initially are very limited. We'll run a model, the initial model, here from the center, and with the capability of the program, we can put it in a shared file. I could take a picture of the screen, whatever means possible to be able to get it to those initial decision makers that are out in the field, because they're making decisions on what's a realistic containment area for this fire, if at all possible. Where are we going to be able to stop it?
The Pacific Research Platform has convened annual workshops in 2017, 2018, and 2019. Attended by hundreds, including the leaders of the major national networking organizations ESNet, Internet2, and the Quilt. We held workshops for minority-serving institutions and NSF under-resourced EPSCoR states and invited their leadership speakers to increase inclusion and diversity in the PRP communities. In addition, the PRP team has attended major technology conferences such as the annual supercomputing and CENIC meetings. The science engagement team has also created smaller on-campus workshops to engage new members. Providing technical training and expanding our growing PRP community continues to be a central focus of the PRP grant, with both in-depth technology courses, weekly technology video meetings, and detailed documentation on how to get started in the PRP website. To accelerate the rate of scientific discovery, researchers must get the data they need, where they need it, and when they need it. Join the community, collaborate at the speed of light, and unlock tomorrow's discoveries. To get involved, visit pacificresearchplatform.org.